Hi, my name is Ozan Öner, and this is my Physics 212 project. In this project, we are going to measure Planck constant using LEDs and incandescent light bulb. The equipment used for this project are RGB LEDs, a DC power supply, connecting wires, resistors, cardboards, and black and white papers. We use the black paper to cut out the slits in order to the RGB LED to pass, and the white paper as a screen for us to see the diffraction grading. In order to measure the Planck constant, we need to know the wavelength of the desired color of light, and we, in order to find the value of the wavelength, we uh, we make an we make a spectrometer. Our experiment has two parts. In the first part, we measure the Planck constant using LID and obtain Planck constant that way. And in the second part, we use an incandescent light bulb and LID to obtain Planck's constant. In the first part, we linked our RGB LED to a power supply via cables and obtained white light as a combination of red, green, and blue colors. Our setup can be seen in this picture. Then we put the LED near to an slit to let the light pass from it, and we put a CD to diffract the lights into a screen. There are two shapes in the screen. One is the central white peak as the max intensity region of the white light, and the other is the diffraction pattern consisting of blue, green, and red in a cone-shaped pattern. This can be seen in this picture. To calculate the desired color wavelengths, first we use an app called Imagine to calculate the distance between the center of white light and the center of blue, green, and red light separately from the photos we captured. Then, using this equation, we calculated the wavelengths of the blue, green, and red lights. Here, theta I is the angle of incident and it corresponds to the angle between the incoming light ray and the normal to the CD surface. Also, it represents the central peak of the diffracted light. Uh, and theta M is the angle between the diffracted light ray and the normal to the CD. And D is the space between the bumps of the CD. And we calculated the wavelengths of the red, green, and blue lights using this equation. Our results are here. And using this equation and the values we obtained, we calculated the Planck's constant for each color of light. Using blue light's wavelength and threshold voltage, we calculated Planck constant as 7.53 times 10 to the power minus 34 joule seconds, with an error of 30.64%. With using green light's values, we calculated Planck constant as 8.04 times 10 to the power of minus 34 joule seconds with an error of 21.3%. And we and using red lights values, we calculated Planck constant as 5.96 times 10 to the power of minus 34 joule seconds with an error of 10.1%. Then in the second part, we repeated the exact same procedure, but instead of a LED, we used an incandescent light bulb as an light source. Then we used the data from the LED and make an intensity slash wavelength graph for LED, and made the same graph for incandescent light bulb. And putting two graphs on top of each other, we can deduce the wavelength of red, green, and blue colors emitted from the incandescent light bulb. This can be seen in this figure. Then, following the same steps and using the same equations in the first part, we calculated the Planck constants emitted from an incandescent light bulb. Our results can be seen in here. The error corresponding to red light is 5.67%. The error corresponding to the green light is 12.28%, and the error for the blue light is 1.72%. These errors might have happened due to several reasons, but our biggest problem is not having enough dark environment and not obtaining pure white light. Calculating angles is also problematic, so errors might have happened because of that. And most of our errors come from measurement uncertainties and some limitations of the tools we used. For example, we have to measure the positions of the colored light spots from the photos we took with our phones, which is not precise and accurate enough. Additionally, sources of uncertainty include the inability to measure the tilt angle of the CD with high precision, ambiguity in the distance between the CD and the screen, and the lack of exact information on the wavelengths emitted by the RGB LED.